All right, everyone. Let's get started. So yeah, we are here at local time. It's 2:31. So we are just 1 minute past. Hope everyone can hear me right. So good morning, good afternoon, or good evening, perspective to where are you? Thank you for joining us for this webinar organized by the Canadian Geotechnical Society Young Professional Committee. My name is Rajit Ayatna. I am a geotechnical engineer at WSP Canada, based in St. John's, Newfoundland, and I am serving the CGS YP committee as the knowledge lead and will moderate today's webinar with along with Alex. CGS YP committee, we initiated this webinar series to allow young professionals to enhance their knowledge in a range of areas of geotechnical engineering. We successfully conducted 6 webinars so far this year. So if you are interested in listening to past talking, recordings are available on our YouTube channel, and I will post the link in the chat. Before we get started today's webinar, there are few housekeeping notes to avoid any disturbance. Audio and video access has been disabled. So if you have any questions, please use the chat option. It is available. Also note that this webinar is recorded and it will be available later to view on our YouTube channel. The presentation will only take about 40 to 45 minutes, and there will be a brief Q&A session at the end. If you have any questions for the speaker, please type them in the chat and we will take as they appear. So we have a very special speaker today. Our speaker is Dr. Sina Javankhoshdel. I think I pronounced your name right, Sina, from Rock Science. He's a geomechanics product manager, the product manager of slide 2 and slide 3 at Rock Science. He holds his PhD from Queen's University in civil engineering, specialized in geomechanics. Joined Rock Science in 2016 and has done some research and development work on slide 2 and slide 3. He has been the 3D expert modeler at Rock Science since 2018. Dr. Javankhoshdel is an instructor for workshop, webinars, short courses, and customized courses, and a presenter at many conferences. Without further ado, I would like to invite Sina to start his talk on a comparative analysis of 3D finite element method and 3D limit equilibrium method and the impact of 3D versus 2D analysis. Over to you, Sina.
Thank you so much, Ajit. Can you see my screen?
Yes, we can. Yeah, everything's
Okay.
perfect.
Hi, everyone. I'm very excited to be here and to do this presentation. Thanks for the invitation, and I hope we all enjoy this webinar. The title is a comparative analysis of 3D finite element method and 3D limit equilibrium method and the impact of 3D versus 2D. As Rajit mentioned, I'm the product manager of Slide 2 and Slide 3 software and have been working on these finite element limit equilibrium software packages, making models for customers for the past 7 years. So part of this is a, first of all, this is not an advertisement webinar. I'm trying to keep it technical, but obviously I use rock science software to show you what are these impacts and what are the details. And I'm gonna warn you, some of you guys may not agree with what I say and may have questions. I totally understand the different aspects and different thoughts on these concepts because they are very broad. But these are based on our experience at Rock Science and my personal experience, and I'll show you different practical models as well. So, before going to the technical part, I just want to introduce us and to show you some details about Rock Science. We are the world leader of innovative 2D and 3D software for civil mining and geotechnical applications. We have the experience of over 25 years. We have more than 10,000 customers around the world, and we are the world leader, really, of 2D and 3D software packages. We have 18 software packages, different applications, but I'm not going to talk about these, only 4 of them. I'll show you which ones I'm going to talk about. But the more important thing that to emphasize here is the integration between these software packages, which is part of my talk today, because we want to go from 2D to 3D, from LEM to FEM, back and forth, to talk about this and the impact of moving from one application to another application and one method to other method. So these 4, slide 2, RS2, slide 3, and RS3 are the software packages that I'm going to talk about. Rajit mentioned that I was part of the slide 2 team since I joined Rock Science. I developed spatial statistics in the software, and then I moved on to other roles. So part of this presentation is about and coming from a developer in perspective, because as a developer of a software, you need to think general. You can't just focus on a specific thing. So it helps us understand the details more for what our customers need and what they think, what we should do on our side. So let's jump into the presentation. And the other thing before I start is I'm making a case. I'm telling a story here. So I will go step by step to the end, and hopefully we reach a good conclusion. So let's start with simple 2D limit equilibrium analysis and see what's going on there, and then we go further. So basically, when you want to do any 2D analysis, limit equilibrium analysis, you need to do and to have and to consider all these aspects. You need to have a slope geometry. You need to know your geological models, which are the layering, slope layering, soil profiling. You need to know the groundwater condition, the loading of the model. You need to define your failure criterion, which are constitutive models or material models. And then you need to decide about the failure analysis. So here we do limit equilibrium and finite element analysis. We do finite element analysis for the failure analysis part. In limit equilibrium analysis, there are 2 steps that some of you guys might not know that this is actually what's happening. First of all, we compute the shear strength required along the potential failure surface to maintain stability. So the goal in the limit equilibrium is to maintain stability and to calculate the equilibrium condition. Then we compare the required shear strength to the available shear strength. So what is available shear strength? What is coming from? It's coming from your soil properties that you define and the criterion that you define. For example, here we define more Coulomb failure criterion. So you know your available shear strength. A lot of times you don't know your required shear strength, but you know the goal factor of safety goal that you want, and then you calculate your required shear strength. So you know that C plus sigma tangent phi, which is the more Coulomb, and you know the factor of safety, the goal factor of safety, and you want the required. In a slide, you don't know the factor of safety in advance. So you have the required shear strength, you have the available shear strength, and based on the calculations, you calculate factor of safety. Keep this equation in mind. I'm going to use it later on in the presentation. It's a very important equation that we're going to talk about it later. So limit equilibrium analysis in 2D is called method of slices because we can't solve for this factor of safety by only solving the based on one critical slip surface. So this is an unknown problem. So we have to simplify it kind of to be able to solve it for the factor of safety. That's why we divide it into slices to make it simpler. For these slices, let's say we have n slices. Let's see what we have as unknown parameters. We have n normal forces on the base, n shear forces on the base, and also interslice shear and normal forces. The other unknowns that we have, one is factor of safety, one is the location of these forces applied to the base and side of each slice. So there are so many unknowns, 6n minus 2 unknown parameters. How many known parameters do we have? We have 3 equilibrium equations: moment, horizontal force, and vertical force. And we defined our failure criterion, which is more Coulomb failure. So we have n more Coulomb relationships as well. So the total is going to be 4n. We still need a couple of more known things. So we have other assumptions. One of the most important assumptions is all the forces, they are applied in the midpoint of the base of each slice. So Zi is equal to half of the base of a slice. So that gives us another n known parameters. So we are left with n minus 2 unknown parameters. And we need to solve these equations. So that's why we have 11 limit equilibrium methods to calculate factor of safety, all coming from different assumptions that they have to solve these n minus 2 unknown parameters. We focus only on 4 of them: Bishop simplified, Yambu, Spencer, and GLE. Basically, they have different assumptions. Bishop assumes that interslice shear forces are 0. Bishop only satisfies the moment equilibrium. Yambu has the same assumption, so shear interslice force is 0, but it only satisfies the force equilibrium. And Spencer and GLE, or Morgenstern Price, they satisfy all the equilibriums. The only difference that they have is about the direction and the angle of the normal interslice force applied to each slice. Some of the things that it's interesting to know is Yambu always gives you the lowest factor of safety compared to the other methods. And when you use non-circular methods, do not use Bishop, because Bishop only satisfies moment equilibrium, and moment is going to be around the center of the radius. And for non-circular methods, we change this center all the time. So for some models, Bishop cannot give the correct answer. But Yambu and GLE and Spencer most of the time give the most accurate results. How about 3D limit equilibrium? So we talked about this method of slices. So 3D equilibrium, same concept. So basically that one is in 2D, this one is in 3D. Instead of method of slices, we have method of columns. So if you look at figure C, it's one cross section, which is slices in 2D. We give it one more dimension in figure B, normal to the plane of the model, and we create a column like this. So basically the same concept, the same equilibrium concept. However, you have so many forces in different directions because it's in 3D. It's not like horizontal, like normal and shear. So your shear can be in different direction, normal can be in different directions. So we solve in different spaces actually, XY, YZ, and XZ, different directions. I don't know if it still exists in other software packages, but it used to be for the 3D limit equilibrium originally years ago, you had to define the direction of failure, because in 2D you say, okay, left to right, right to left. 3D is not like that. It's more general. So you had to define direction of failure. But now, for example, in a slide 3, we give you the direction of failure. So I'm not going to go through the details of these equations. The thing that I want to mention that in the 3D limit equilibrium, you calculate factor of safety in different directions. But the assumption and the equilibrium assumption is if fx, you have fx, fy, fmx, fmy, different moment and force factor of safety, they should all be equal to satisfy the equilibrium. And that's the main assumption in the 3D limit equilibrium analysis. So these are the basics of limit equilibrium, Yambu, Spencer. If you go to any software package, if you go to any hand calculations, they're all the same. You don't change the Bishop formula, you don't change the Yambu formula, they are all the same. But something that's very important that you don't deal with it in the finite element analysis is the search. So as I showed you before, you have to define your slip surface. You have to assume a slip surface first in the limit equilibrium, then divide it into slices. So how do we find that slip surface? How do we define it to be properly find our critical slip surface and to represent our critical slip surface? That's the search method that comes to mind. So I know, and you know, that most of the standards are based on circular search method. This is a nice table, shows you for what type of problem, what type of search method you should use. These are based on the options that we have in the slide, but it's in general, basically. So for homogeneous slopes, circular is fine, but you can tell me if you have seen any homogeneous slope in your experience. With material models without weak layers, multi-material models without weak layers, still circular can be a good starting point, but you should a little bit take it to a more complicated method like auto-refine that we have in a slide or cuckoo search. I'll explain about those. These are weird names. I'll explain them. If you have a weak layer, circular doesn't really help, and you have to go to more advanced methods. We have block search, which a lot of people use for weak layers. You can use that one as well, but it requires a lot of expertise. But if you have anisotropy material, circular doesn't work at all. Or you have multiple weak layers, circular doesn't work at all. So you have to go to more advanced methods. What are these methods? Particle swarm, cuckoo search, simulated annealing. So part of my presentation is about the researches that we do at Rock Science about different things. I will explain as I go further. But these meta-heuristic methods, these are the methods that we borrow from other fields. For example, cuckoo search is applied in mathematics in different fields and is the way that cuckoo birds, they put their eggs in other birds' nest, and there is a flow, there is an algorithm. We use that one for geotechnical application and find critical slip surface. Particle swarm, simulated annealing, the same thing. We borrowed it from nature. What are they? They are basically non-linear equation solvers. We use this kind of algorithm flow that they have to solve nonlinear equations. What is our nonlinear equation here? Factor of safety equation is a nonlinear equation. So we use these methods to solve the factor of safety equation, and they work really, really well. This is, for example, about particle swarm in 3D. Basically, particle swarms, you throw particles throughout your entire model, and they try to go to the point with the lowest factor of safety. Here, this is a temperature map. So they try to go to the lowest temperature. but the same is for factor of safety. They try to go to the lowest point. So that's how they work, actually. But we found that these meta-heuristic methods, especially in 3D, they're not enough because they are limited to spheres and ellipsoid shapes, which are limited shapes. Your failure surface might not be that shape. The search in the big area is very coarse. Like these particles, you can see how many particles you throw. You cannot send particle to every centimeter of your model. That's going to take forever. So you have a limited number of particles to throw in your model to find the lowest factor of safety. And these meta-heuristic methods, they lead to overestimate factor of safety. So if in any software you only use meta-heuristic method, your results are overestimated. So period. Like it's not something that I make up. It is real. That's why we did some research in-house at Rock Science. A lot of these we did the research in-house. And we came up with a method and say, okay, let's say this is figure A is a sphere shape. We can change this shape, we can play with it to locally optimize the critical slip surface that it found. So to do that, we defined a control net, as you can see in figure B and D, and play with this control net. How to do that? We define a mathematical concept called NURBS, or non-uniform rational basis splines, or splines, to change this sphere and ellipsoid to a spline first, and then a spline has the ability to be changed. So we do 5 more steps on top of these meta-heuristic methods, which are advanced anyways, but we do 5 more steps. So we move these, we scale and shift this net, we modify the curvature, we modify the frame up and down, we modify the frame elevation on each side, we bubble gum the stretch, like move points towards the end, and we locally optimize the critical slip surface. If you want to see what is the influence of this, here's an example. The yellow material is a weak material, anisotropy weak material. So our goal is to have a failure surface follow this weak layer. We are all geotechnical engineers. When we have a weak layer, failure surface should follow this weak layer. So if in practical case the slope fails, it fails along that. So failure surface should be along that weak layer. So we have 2 surfaces here. The blue one is after this surface altering, which is a local optimization. And the one with the shadow is before that. Clearly, the one with shadow didn't follow the weak layer. That's meta-heuristic search, by the way. But the blue one is consistently follow this yellow material. What is the difference? With meta-heuristic particle swarm factor of safety 1.66. With surface altering, so more alteration, 1.3, 20% difference. And that's a real difference. So in a slide 3 and slide 2, this option is default, surface altering. Some users, because it takes longer, they say, okay, forget about the local optimization and only do meta-heuristic because meta-heuristic is enough. If I receive a tech support like that, I don't even look at it because I am telling the user directly that this is inaccurate. So if you don't do local optimization, your results would be wrong. And we always confirmed our results with finite element, and we got the same failure mechanism, same answer using finite element. I'll get into that later. So far, what I showed you to change meta-heuristic to local optimization, we changed them to spline search methods. So basically, these surfaces in 3D, you have to solve some parameters. For example, for spheres, you have 5 parameters: start point, end point, and the rotation of the sphere. It's similar to circle. Ellipsoid, you have more parameters. You have some angles and radius, because the radius is not constant, and you have more parameters. But we found that the sphere and ellipsoid, even though we try to change them to nerves or splines, they don't work very well. So that's why, again, we developed a method in-house um, called spline. So basically, that's how it works. Without even assuming any failure shape, like a sphere or ellipsoid, we directly solve a spline surface. So a spline surface has 11 parameters to solve. Compared to the other two, it has way more parameters, but it is very flexible. So instead of starting from a sphere to an ellipsoid to a spline and then surface altering, we directly start from spline, which is more complicated, but way more flexible. By the way, you can go to my Google Scholar. All these, we publish them in journals. So this one is a recent journal, Nerve Surface Altering Optimization in International Journal of Geomechanics. So all the research that we do at Rock Science, we publish them. So you can go to my Google Scholar or ResearchGate and download these papers to read the details. Now, we wanted to go one step further because we found that some cases we have another problem. Let me show you the problem. In traditional limit equilibrium method, we are only looking for this global minimum. This is a nonlinear equation of factor of safety that I talked about. We are only looking for this global minimum. But good luck with that, because there are a lot of local minimas that even advanced search methods, they might get trapped in these local minimas and they don't give you the global minimum. How do we solve that? So we came up again in-house with a method called multimodal optimization. Multimodal optimization, what it does, it doesn't look for global minimum. It looks for all the local minimas. Obviously, this global minimum is one of them. And the software is gonna give you all the minimums. For example, 3 minimums. It's not filtering the search, it's a search itself. So it's based on the particle swarm search. It has its own algorithm separate from the main algorithm, and it looks for local minimums, and it gives you like 3 or 4, depends on what you choose, the minimums. Another example, this is an open pit. The yellow region again is a weak material. This is kind of symmetric, so you can expect to have a failure on the north side of the model and a failure on the south side of the model. If you do traditional limit equilibrium, it only finds 1, which is a factor of safety of 1.002. If you focus your search on the other side, it gives you 1.12. To me, 1 and 1.12, they are both are critical because they are way lower than the standard factor of safety. They are not failure, but they are low. If you run multimodal optimization, it not only gives you 1.004, it gives you something with a different failure mechanism of 0.997. It means that 1.004 was a local minimum. It wasn't a global minimum. And also it gives you this failure on the other side of the model. So it gives you 3 instead of 1. We always run again with finite element. So if you run it with finite element, it gives you 1, 2, and 3 on the other side. So you can see how we match the results with finite element. Let's discuss 2D versus 3D limit equilibrium based, and then we go to the next step. When do we model in 3D in general? That's a very interesting question. We were always asked about this. When should we do 2D modeling? When should we do 3D modeling? What is the difference? That's part of my talk today. So basically, if your geometry is 3D, if you have an open pit mine, you cannot do it in 2D. Like you cannot use 2D modeling to model a 3D geometry. If your failure mechanism is 3D, so basically normal to that failure mechanism does not give you a proper answer. If you have anisotropy surfaces not aligned in the 2D cross section, if you have material changing spatially, if you cannot represent your model with a couple of 2D sections. If you have 2D sections, but if the spacing between 2D sections are large, those properties change significantly. So it's better to do it in 3D. The most important one is if your boundary conditions are 3D. Sometimes your seepage boundary conditions, your loads, your supports, they are all 3D. You cannot represent them with a 2D model because 2D, what it assumes that, for example, if you have a load, your load has an infinite length normal to the plane of your model. If you have support, they are all spaced equally normal to your model. So you cannot change them to like, for example, non-uniform spacing for supports. The other question is how conservative, because a lot of people, yeah, we do 2D and it's very conservative. We are okay. We design a factor of safety of 1.5 for 2D. Sometimes being conservative or showing that 2D is conservative is not the solution because it's sometimes 2D cannot capture proper behavior. That means that your 2D results are wrong. It's not conservative. Some people claim that 3D models factor of safety should be more than 15%, about 30%, 40% higher than 2D. With the assumption that 3D searching is localing the true global minimum. But you should question what methods are using, what surface shape they are using. Should we design a slope using 3D results or not? So these are the questions that we need to ask. So I'll go through a couple of examples. I see questions. I can answer questions along the way, but I can leave them to the end. I think it's better to leave them to the end to that I can keep track of my time.
That's right. Yeah.
Okay, sure. So let's look at the first example, simple slope with a weak layer defined. So this is an extruded model. Extruded models, by the way, should act exactly like 2D models because everything's the same. It's just it's like bunch of 2D models, they are exactly the same. Because everything is symmetric. So we looked at the results, the difference is about 6%. Next model. MSC walls, again extruded, difference is about 6%, 1.08 compared to 1.01. For MSC walls, the reason for this difference is the shape of the slip surface, because sometimes you show external failure mechanism for a slip surface, but external doesn't mean anything in 3D because 3D a slip surface must intersect the reinforcements. It's not like 2D that is a line going behind the reinforcement. We don't have such a thing. Open pit models, 5% for this model. Coal mine, these are complicated models, 5% compared 3D compared to 2D. Another complicated open pit mine, 12%. And these all depend on where you take your 2D section, by the way. Your 2D section, if you want it to be more accurate, it should be right in the center of your 3D failure surface. Otherwise, you can't compare even the results because 2D is going to give a totally different factor of safety. But in the middle of your 3D failure, sure. So, first of all, the difference is way smaller. The maximum difference that I've seen is 15 to 20% maximum. Local optimization is very critical in both 2D and 3D to be able to compare. Design should be a combination of 2D and 3D. It's not just be based on 3D or 2D, and we always recommend to calibrate your results with the radar data as well. And do not assume that you can use less support because 2D results are conservative. Not unless you are extremely sure that you have the correct global minimum in 2D. So that's a very important question. Now, we compared these examples that I showed you with finite element as well. So for 3D, you can see that 3D limit equilibrium 1.45, finite element 1.45 as well. Now I want to take you to an example. This is a model that I created years ago, but this is a tailing dam that failed in Brazil, killed a lot of people. 160 people got killed and others 160 got missing. So to show you what happens, this is the tailing dam and this is the time that it failed. You can see how it filled all these channels. So I modeled it using a slide tree. I use a spline search, which is this new search that I talked about, particle swarm optimization, and I use multiple option, which is a multimodal optimization. I calculated C-page analysis and did the C-page analysis in RS3 and brought the C-page result as a grid into a slide tree. So we have 3 different failure surfaces for this model, all 0.93, one failure surface, 2 failure surfaces, and another one which is totally different failure surface. So some sort of L-shape mechanism. That's at the time when I did this model, we didn't have a spline, and I couldn't capture this big one because a sphere and ellipsoid cannot capture this. So this is the main failure mechanism. This is a base cohesion, so it shows that this is going through 3 different materials. And this is a cross section. You can see that in 2D cross section, we have 2 different failure surfaces as well. That's why I defined 3 sections in this model, all 2D sections, and looked at the results. So section 1, section 2, and section 3. 2 of them, they have multiple mechanisms similar to what we observed. And section 3, because it is, I think here, it only captured section 2, sorry. Section 2 is in the middle. It couldn't capture the multimodal mechanism. So you can see that. And also comparing factor of safety, 3D gave 0.93. 2D is very close, but this one is way lower. Again, close. Depends on where I took the section, the difference might change. That's what I have been talking about. And these are the 2D results on top of the 3D results. And you can see that the 2D failure surface captures very nicely the 3D failure surface. But how do I be sure that these are true failure surfaces and failure mechanisms? Should I trust to 2D and 3D limit equilibrium, or should have something else to verify the results? That's the main question. So that's why we always do and we always recommend to compare your limit equilibrium results with the finite element results. There is a belief in the finite element world that limit equilibrium is not a good method and you cannot capture proper failure surface and failure value. But we moved that limit equilibrium they're talking about is circular Bishop method for 30 years ago. We moved these limit equilibrium concept way further than limit equilibrium with complicated search methods, with complicated optimizations. So as long as you use the same material constitutive model, limit equilibrium is limited to elastic, perfectly plastic. I know that. So as long as you use the elastic, perfectly plastic with 90% of the people who do a slope stability use it, you should get the same answer using finite element and limit equilibrium. There are exceptions like toppling. If you have support, I know these are different. But if you have simple models or a model like this tailing down, there is no reason that you get a different answer using finite element. So limit equilibrium pros, it is the most commonly method used in practice because it's simple, quick analysis. You can do sensitivity analysis, and you don't really need a lot of information. You just need a couple of parameters, and that's it. Cons, the failure mechanism should be assumed in advance, but with the spline I showed you, we are very flexible. You don't have to really be worried about that part. The main cons of limit equilibrium is neglecting a stress-strain behavior, and it doesn't provide you any information regarding deformation. That's the problem. This is a quote from Bishop, and I told you to remember an equation. It says, the factor of safety is defined as the ratio of the available shear strength of the soil to the required maintain equilibrium. The shear strength mobilized, therefore, is equal to this. This is based on a method in the finite element analysis called shear strength reduction method. So we are actually doing the same thing in the finite element analysis, similar to limit equilibrium. We are reaching to equilibrium and we are using shear strength reduction method. So this is for more Coulomb. We are reducing the failure envelope, more Coulomb failure envelope, with a factor called reduction factor. And we calculate like factor of safety. That's how we do it. We reduce the parameters by a factor called reduction factor. We compute the finite element model. If the analysis fails and does not converge to a solution, we reduce the factor and recompute. If it converges, we increase the SRF factor and it recompute. Factor of safety is this reduction factor that initiates the failure, meaning that if you increase it a little bit, the solution doesn't converge. So, what are the disadvantages of this method? First of all, computation issues. Limit equilibrium is way faster than finite element. There is a quote. This is being recorded, but it's okay, it's everywhere. About finite element analysis, people say garbage in, garbage out. So if you don't have enough knowledge of your input parameters, you get wrong results. I have a quote from someone. He said we sent results of our lab to hundreds of consulting companies. The most accurate results came from finite element. The least accurate results came from finite element. Depends on the level of expertise that you have. The other problem is definition of instability. In limit equilibrium is equilibrium. In finite element is numerical convergence. Sometimes you have a failure, but that's a numerical issue. It's not the actual failure. And the other problem is sensitivity analysis is difficult. But you should use this method to compare the results of limit equilibrium. That's a verification part. And it gives you information about deformation. It's very robust. It captures failures by stress. And it is flexible compared to limit equilibrium analysis. So these are all the material models that we have in a slide, and these are material models that we have, for example, in RS2. So they should match if you want to get the same answer. Same model. This is, I need only 1 or 2 minutes. This is the tailing dam model, section 1. We get one failure surface from finite element, 0.88. So this is matching. You can see that they are matching. Second failure mechanism in section 2, deep failure mechanism, limit equilibrium, and finite element, very close failure surface matching. Multimodal ones are very interesting. So here you can see there are two. One is here and one is here. So this is one and this is another one. So finite element actually captures multimodal, and now in a slide we can capture multimodal optimization, which is very important. And section 3, again, one failure, two failures. So it captures both, and factors of safety they are matching. Let's go to 3D. This is the slide 3 that I showed you. Now let's compare it with the 3D finite element. 0.96, 0.93. Very close values. And just look at the shape of the failure. In a slide, we had to do multimodal to capture this L shape. In finite element, it gives you already. It's a L shape. So that's the difference. That's how you confirm the results and you look at the results. This is the maximum shear strain, and this is safety map. We call it something like safety maps, ISO surfaces, which gives you surfaces with the maximum shear strain. So some 3D ISO surfaces with the same maximum shear strain. So this is the same shape that we got in the slide 3. So the conclusion is, first of all, depends on where you take your section, depends on your model. Your 2D and 3D results might be very close, might be maximum 15 to 20% apart. 2D and 3D limit equilibrium, that's about 2D and 3D. Finite element and limit equilibrium doesn't matter, 2D or 3D, as long as you use elastic perfectly plastic material, the results should be very close, similar to what I showed you here. And we use finite element to verify the advanced limit equilibrium results. Thank you.